Hello, and thank you for attending our Solid Edge Generative Design webinar today. First, before we get started, I wanted to give you a quick reminder that we are consistently adding new Solid Edge and NX, CAD, CAM, and electrical content to our Prolim YouTube page. If you aren't already, go ahead and give us a follow on our YouTube channel so you get access to this content when it's dropped. So a little bit about myself, if this is our first time meeting. My name is Aaron Creech, and I've been with Prolim for over 4 years now. I have over 20 years of end-user design engineering experience, much like many of you on the call today. During that time, I've worked in the manufacturing, architectural, and automotive design industries. I've built a strong working knowledge of most popular 3D CAD design softwares, such as Inventor, CATIA, SolidWorks, several Autodesk products, and obviously Solid Edge. As a senior application engineer with Prolim, my primary focus is Solid Edge Mechanical, MCAD, Solid Edge Electrical, ECAD, and Solid Edge manufacturing portfolio products. My career interests include generative design, additive manufacturing, and process improvement, or Kaizen. So here's a quick look at our agenda for today. We'll give you a quick introduction into generative design. We'll highlight some of the major benefits, as well as an overview of the generative design process and how Solid Edge leverages different types of models to achieve our goals. We'll review the user interface as well as some common workflows. Then we'll walk through a demonstration of building a generative design study. We will have a quick Q&A at the end of this session to answer any questions or comments that you may have. We just ask that you save all your questions and comments till the end of our presentation. So let's go ahead and get into it. Let's start by introducing generative design. And one way to do this is to compare generative design with traditional mechanical design. With traditional design, the first step is to understand the requirements for the design, and then to apply good engineering practices and your experience and use traditional 3D CAD software to design a shape that meets your requirements. You then validate the design using computer-aided base stress analysis and/or using physical prototypes. And you may need to loop back to modify the design. With generative design, the first step is the same. You need to fully understand the design requirements, but the next step is to input these requirements to a generative design study, and then let the software and the computing power to create the best shape that meets your requirements. Validation in terms of stress analysis is performed as an integral part of the generative design process. Additional validation may still be required. One example of a manufacturer who is benefiting from generative design is Hall Designs, a startup manufacturer based in San Diego, California, that designs and manufactures components for off-road racing cars. The components they deliver to their customers are subject to extreme conditions, have a high design content, and are manufactured in low volume production runs. Hall Designs were able to replace 4-part steel welded assemblies for a gas pedal with a single component designed using Solid Edge generative design. The new component was manufactured using additive manufacturing and is 25% the weight of the original, but is equally as strong. Hall Design is using their proven capabilities and this new technologies to win new customers and grow their business. Let's look at the potential benefits of generative design offers to manufacturers. The first is the possibility to reduce cost per part by reducing the amount of material used in a specific component, and therefore material cost. This is particularly important for part manufacturers in high volumes, but have a significant impact each on a batch production and one-off parts. The second is the opportunity to reduce your manufacturing cost. Generative design results in a single solid mesh body that can replace a multi-component fabrication such as a welded assembly. This reduces your need to spend money on jigs and fixtures and on welding materials and highly skilled welders. These single body parts can also be manufactured using the latest additive manufacturing techniques. This reduces the need to design and manufacture expensive tooling. Another opportunity is to reduce component weight while maintaining the strength. Where the component is a moving component in a machine, lighter weight improves the efficiency of the machine and reduces energy consumption. And for vehicles and airplanes, lighter weight components also reduce energy consumption and can enable manufacturers to meet stringent regulatory requirements for the efficiencies of their product. Generative design is a different approach to design that uses advanced software and computing power to optimize your design. It introduces the possibility to create radical, different looking designs. The result of generative design can even be used as a source of new design ideas for your product. It also creates unique, organic looking designs with an attractive appearance that help the product stand out from the competition. Inputting the design requirements is a key part of the generative design process. Some of the key steps are defining the design space. You start with a basic solid body that represents the size of the component and the shape or volume that it can occupy. Defining specific geometry that is essential for operation. Locating points, bearing surfaces, keep out areas, essentially your envelope. Defining loads, including type of load, direction and value, safety factor, material, and target weight. Generative design takes into account all the requirements mentioned previously. It then applies finite and element methods and computing power to analyze hundreds of potential solutions and offers the optimum shape that meets the design requirements. The result is a mesh or facet-based 3D CAD model. Now let's talk specifically about Solid Edge's solution for generative design. Solid Edge offers a unique generative design solution that enables quick creation of optimized, lightweight product designs. It uses the latest topology optimization technology for fast and accurate design optimization. It's easy to use, intuitive solution with simple ribbon bar that guides the designer through the required steps. It creates mesh-based solid body models with smooth surfaces that are ready for manufacturing. And you do not need to dedicated analysis to run the software. It is a tool for all designers. And a unique aspect of the Solid Edge solution is how easy it enables you to integrate the mesh-based model created by generative design into your production development process. For example, you can use standard Solid Edge commands and add features to the component, cutouts, holes, bosses. You can then align and constrain the components correctly in the Solid Edge assembly. You can create 2D drawings of the 3D models, and you can manufacture the component using the additive manufacturing or traditional machining methods. At this point, let's take a moment to present some background information about the two types of CAD models that we have mentioned: BREP models and mesh models. A BREP, or boundary representation as a model, is an exact mathematical model of a 3D part. It includes definitions of the topology, faces, edges, and vertices, and geometry, surfaces, curves, and points that make up the 3D part, with some intelligence to say which side of the surface is solid. Most modern 3D CAD software, including Solid Edge, uses BREP as a primary method for defining the model geometry. Mesh-based models, also referred to as faceted or tessellated models, use flat triangles to present geometry in an approximate lightweight format. A sag parameter is used to control the approximation by defining the maximum distance between the triangle and the surface. Here you can see the dialog that is used to set the parameters in Solid Edge. Mesh models are created by FEA software, reverse engineering, generative design, specialist mesh-based modern modelers, and are consumed by 3D printers and additive manufacturing. Solid Edge supports both BREP and tessellated models. In fact, Solid Edge now supports convergent hybrid modeling, which gives the user the ability to model directly onto a true mesh or faceted body, speeding up the design time by eliminating the need to convert the mesh body to a BREP body just to generate modeling features to the design. The chart shows how a common CAD formats, both neutral formats and proprietary formats, use BREP or mesh body, or often a combination of both. For example, IGES is a BREP format. STL, or stereolithography, used to transfer data to 3D printing or to store lightweight representations of a 3D model in a mesh or tessellated format. Most current CAD systems use a BREP format to define their CAD models, but many, including Solid Edge, also support tessellated formats. An important aspect of the Solid Edge approach to the design is that it enables you to combine mesh models and BREP models in one environment. Convergent modeling is actually included in the Parasolid graphics kernel that is developed by Siemens and used by Solid Edge and many other CAD solutions. In addition to supporting generative design, convergent modeling also supports reverse engineering, the process of scanning real parts to create CAD models. This process also results in the creation of a mesh-based model. And for manufacturing, new additive manufacturing techniques are also based on mesh models. So the capability that convergent modeling gives you to work more efficiently with mesh-based models, for example, adding features to them using standard Solid Edge commands, has a big impact on your ability to take advantage of the new additive manufacturing technologies. Let's take a look at the core areas of generative design. As a quick example, we'll first take a look at the sewing machine and focus on its internal mechanical components. These components are typically modeled using several features that define the required geometry, all in order to make sure that it's strong enough to support all of the components that are connected to it. Now consider a process where you only create a basic shape, as you see here, and let generative design figure out the rest. Generative design never adds material, only removes it. So it's important to define areas of the model that need to be preserved. Not only can we create loads and constraints, as we're doing here, to ensure the model that can withstand the standard operating conditions, but we also have the capabilities to select areas of the model that need to be preserved, such as mounting and locating features. Once the model's design requirements and constraints have been defined, generative design then takes this important information to generate a very smooth, organically shaped model that fits the design needs that you're looking for. Not only does generative design save significant time, but it also helps reduce material costs by reducing the weight. The power provides a very smooth, organic, mesh-based body that is ready for additive manufacturing. Generative design is useful in many different industries, including aerospace and defense, automotive, and more. As an example, consider this simple bearing block. Using this intuitive process, many revisions of the design can be quickly generated, helping you achieve the best possible lightweight solution for your needs, and yet still make sure it's strong enough to withstand the workloads it will face during operation. As another example, let's consider the Hall design mechanical pedal assembly we just discussed. Currently, the pedal itself is made up of 6 different fabricated parts that are then welded together. This can be an expensive process. While we're interested in reducing material, weight, and in manufacturing and assembly costs, while at the same time ensuring structural integrity. This is a perfect application for generative design. To start with, we'll replace the pedal assembly with the basic shape of the model. While moving the pedal in its basic range of motion, it becomes apparent how the design is supposed to work. It helps us better understand what aspects of the part's geometry are important for the pedal to work correctly. Now that we have a better understanding of how it works, we can begin to set up the generative design process for this part. We'll edit into the part, hide any background components. This lets us focus more on the design of the part itself. Generative design is fully integrated into Solid Edge, and all of the commands are right at your fingertips. The command ribbon presents 10 key commands in a generative design for a logical sequence, guiding the user through the steps needed to complete in order to set up and run a generative design study. First, we'll just need to ensure the material is defined. And once the study is created, we can go through the process of selecting and preserving regions and areas of the model that we want to keep. Here we can select an offset value which will preserve the whole and of the embossed geometry. It's obvious where the focus is to be applied on the pedal. The direction of the force can easily be set by using the synchronous steering wheel. The volume can then be defined along with an offset. The final thing to do is to set the constraints of the model. So for this study, we'll set a fixed constraint on both holes at the end of the bottom pocket. And again, we'll define a quick offset. We'll also fix the rear pivoting boss. After defining all of the study options, we are ready to generate our new design. The study dialog gives us access to the slider bars to control study quality and targeted mass. For this study, we will reduce the mass by 20%, as well as consider our factor of safety. Once the study is complete, we can look at the results. Here we can see that the areas of the model where the stress is concentrated just below the pedal. Remember though, we're still within our allowable stress for this part, given our factor of safety. Here we can make some final adjustments to reduce the mass a little bit more and see what the results look like. And as we can see, most of the material being removed is from under the pedal structure itself. Depending on the user's preferences, multiple studies can be created, and each study's settings are easily accessible through the edge bar for quick changes. This process makes it easy to adjust any parameters in order to get the best results as possible. Let's make one last quick change to the pedal in order to give it more strength and stability. Once again, there is as simple as just selecting the geometry that we want to preserve and generating the study again. Select this edge. This time we'll actually reduce the material by 60%. Now we can see that there's significant material removal, and yet super smooth mesh model has enough strength to withstand the force it will be put under in everyday use. On the background components gives us a clear understanding of how our new pedal fits into the current design and interacts with the other components. A huge advantage in using Solid Edge to create and work with these generative designs, which are essentially mesh models, is when it comes to creating additional features of the design that we may need. With Solid Edge, adding and removing material is simple and fast. For example, a cutout can be added for the purposes of adding a bushing. The use of standard modeling tools makes this process quick and easy by picking up on some of the background parts in the assembly. Next, we'll go ahead and add a feature to our part. In this case, we'll add a part number to our part. We'll create some quick text and then extrude it into the design. The power of Siemens convergent modeling techniques available in Solid Edge provides the engineer with the ability to further design the mesh models fast and easy. Returning back to the top level assembly, we can see the finished design of the pedal in motion with the rest of the assembly. So generative design gives us the capability to generate low-cost, lightweight mesh models that can then be modified using convergent modeling techniques. The only question that remains is how can we manufacture these kind of models? Let's go back into our pedal design and answer that question. Solid Edge provides us with the capabilities for you to take your design directly into the additive manufacturing process with just a few clicks. The 3D Print tab provides us with several options to get our designs manufactured. We'll start by previewing our model. This allows us to check on its quality and then adjust its facets if required. If you have access to a local 3D printer, then your parts can be printed right from your desktop. We can adjust the layout and the orientation of the part. The Settle option uses kinematics to drop the model on the printer bed in the best orientation possible. We can then define properties, adjust overhang material supports that may be needed, and then finally select our material. Now, if you don't have access to your own 3D printer, or if you want to apply some not so common 3D printing materials, such as steel, aluminum, tungsten, or ceramics, Solid Edge offers a capability to order these 3D prints through an online service called 3YourMind. Through this integrated interface inside of Solid Edge, you can check the printability and scale of your model. Then browse through different material options. We can use filters if needed, and these are all included in the price, print methods, and lead times. So once we go through and select our preferred material, we can then decide which company we want to produce our part, allowing us to quickly and easily get our parts produced in the quickest time possible. So to quickly recap, Solid Edge Generative Design creates mesh-based solid bodies with smooth surfaces that are ready and ideal for additive manufacturing processing. Solid Edge supports both STL and 3MF file format outputs, so you can design, prepare, and manufacture all right here inside of Solid Edge. So in summary, we reviewed the process of generative design along with some of the major benefits that it provides designers, engineers, and companies as a whole. We saw the power of how Solid Edge Generative Design provides you a quick and easy solution to some of the everyday design problems, leveraging these benefits to make your designs that much more efficient and cost effective. Thank you for your time. So at this time, we'll take any questions that you may have. And if there are no questions, please feel free to direct any further questions to the contact information you say here. Thank you for your time and have a great day.